I'll start off our science talking about the science of dipping artesian aquifers. These include for the major aquifers, these are the Trinity, the Carrizo-Wilcox, and the Gulf Coast are 3 examples. But we have minor aquifers such as the Hickory sandstone that also fits this model. And then, truthfully, all of our aquifers have elements of artesian pressure in them, even the Ogallala. So when you're talking about artesian pressure and these dipping aquifers, it's really important to do a couple of things. One is, the first one is realize the difference between pressure and storage. Those are 2 different things. We also want to keep in mind the regional nature of these aquifers. And I talked about pressure is distinct from storage. And then also the economics of increased supply. How does that economics factor in? And lastly, a concept that is common to every aquifer on Earth, the necessity to reduce storage, to capture recharge, and create sustainability. So what is pressure? Well, here's an example of a tube or a pipe that we filled up with water, and we put a little tube in there. And oh, sorry. Let me get this straight here. This tube fills up with water equal to that level. And if we take water out of this pipe, the water will flow down this big pipe and push the pressure pushes the water back up, but we're taking water out of storage right here. So that's a common little pipe model. Believe it or not, the Edwards Aquifer acts in the San Antonio region where there's high transmissivity. It acts very much like a pipe. The resistance of water moving through this pipe is very, very low. And the Edwards has artesian sections that are draining storage up here, and the springs are located up at this top part of this pipe. So that's how the Edwards kind of correlates to this. Now if we move to a Gulf Coast section of our discussion here, this is the Jasper Aquifer down in southeast Texas. The Jasper, the outcrop up at the top of this slide, that's where the sands intersect at land surface. They're exposed at land surface. That's where rainwater seeps into the ground. And then we have the dipping sand into the subsurface called the subcrop in geologic terms. That's really the artesian portion. So if we just look at an idealized dipping sand aquifer, we have the water that is the aquifer in the blue part. That's where the storage is. We have a confining clay zone that sits on top of this that seals this water. And then we have younger units throughout the Gulf Coast, the Carrizo-Wilcox and the Trinity. In the deeper zones, you have shallower units on top. They're actually separate. And so we have rainfall that comes in and fills all these sands up with fresher water. This water up here at the outcrop is causing, that with depth, is causing this increase in pressure as you go down. And it's just the weight of the water as you go deeper. If we put a well into this artesian zone, the water will rise up this well and again equilibrate with the outcrop water level. That was the case with no pumping. When wells were first drilled in these formations, because land surface dips to the southeast towards the Gulf of Mexico, we get shallower in elevation. When they drilled wells into these deeper zones, these wells flowed all through the Trinity, the Carrizo-Wilcox, and the lower elevation zones. And the reason is because out to the northwest, the outcrop was at a higher elevation, providing that pressure drive. And when we go ahead and pump this aquifer, we'll put a couple of other wells here that won't be the pumping well. The pumping well will be here in the middle. It starts pumping water. These pressure waves and reduction of pressure start radiating outward in the formation. The pressure waves radiate outward relatively quickly compared to, say, a water table depletion well, and they can also span great distances. In this case, within about 1 year, this pressure reduction wave has reached out 30 or 40 miles and reached up to the outcrop of the aquifer. The water levels in each of these wells now has gone down, and we can draw a little black line on top of this map to say, well, that's the new pressure level that exists down in these saturated sands. We'll highlight that with a yellow zone there. So that's the area of reduced pressure. What we haven't done is change any of the amount of water down here to speak of. All the water is still there. And that's a very important characteristic to understand, is that this isn't a reduction of the amount of water, it's a change in the hydraulics of water moving and the resistance of water trying to move through these sands. Because water only flows downhill or down pressure or to lower head, we have to lower the water level in this pumping well to move water to the well. Now, the water is moving through this formation very slowly, even while it's operating. If you move any little bit of distance away from a pumping well, the water might be moving 10 feet per year. So even today, we're still pumping geologic age water, even while we're trying to induce movement from the outcrop towards the well. I talked about the extent of the pressure reduction. Here's an example of the Jasper. If we put a well field in North Harris County and produce 20,000 acre feet per year for 30 years, this is the example of the type of pressure reductions that can occur or be predicted to occur in that formation. And they radiate out, 50, 60, 80 miles along strike, parallel to the outcrop, and then a shorter distance because the pumpage is located closer to the outcrop. The outcrop buffers the reduction in pressure. So any of the historical water level maps, you'll see this same geometry will come into play. If we go to the northern Trinity and we put the same well field centered in McLennan County, we'll get this type of pressure reduction. It's regional in nature. It's, in this case, we're spreading out even farther. We've got higher cones of depression right near the well field because the Trinity transmissivity is smaller, but we're still getting this regional effect of pressure. Ironically, these sorts of maps helped create county-based groundwater districts. And the irony of that is prior to 1995, the state could only create groundwater districts whose boundaries were coterminous with the boundaries of the reservoir or the aquifer subdivision. Today's vernacular, you might say, the common reservoir. A map like this led the state to rule in late 1980s that Bastrop County was not an appropriate area for management of the resource, and a groundwater district was denied. After that, the legislature decided, well, we'll relax that requirement for us to have reservoir-based regulatory areas. We can have county-based groundwater districts, but they have to participate in groundwater management areas, or the proper areas to manage. So we're still working through that process and how to create regulatory frameworks in that structure. If we move to the economics of artesian pressure, this is just a kind of a hypothetical generalized graph to illustrate a few points. This graph doesn't consider the cost of groundwater rights, if there are any, the cost of transportation if you're moving the water long distances, or the distribution cost to move it through a distribution system in a city, say. But a couple of key points that it does make are the cost of artesian pressure reduction is extremely modest. It's about 10 cents per 1,000 gallons per 100 feet of decline of pressure in a well. And that economic relationship holds until you get into large percentages of artesian pressure decline. When you start eliminating all of the pressure and then start desaturating the water table or the pore water storage, you start to enter into an exponential economic relationship. The farmers in the Ogallala and the municipalities in the Ogallala, they are faced with these same economics. So the key point of this is there's a lot of concern about protection of historic use and protection of artesian pressure. But the economics justify greater reduction in pressure and greater supply because the costs of the pressure are so modest. So here's our cross-section again that shows the reduction of pressure and our relationships. If for some reason we start pumping this well at a lower rate, the pressure will just rise or increase. And it's because water is still flowing down from the outcrop and it just rebuilds and rebounds this pressure. So a more important thing is what about the storage depletion up here in the outcrop? That's the source of the water, which leads us to Charles Tice. He wrote a paper in 1940, talked about capture of recharge. Here we have differentiations of natural discharge. That groundwater discharges naturally, spring, seeps, transpiration, and evaporation, versus discharge by wells. Here's an example up in the outcrop where prior to well development, the system is in a state of dynamic equilibrium, and we have spring flow discharging to rivers or through creeks. We have direct evaporation from the groundwater evaporating upward, and we have transpiration. As we produce water, what we must do, what happens in every aquifer, is we reduce storage in the outcrop. That's the first source of main supply. We're neglecting vertical leakage in this model, but the main source of supply is reduction of storage. When we do that, we reduce the natural discharge. The evaporation goes down, the transpiration goes down, the discharge of springs go down, but in commensurate amounts, we capture more of this water in wells, and it provides the sources of supply now. That's a capture recharge. This phenomenon in these formations is extremely slow. You need to think of it in decades and centuries. It doesn't happen quickly, not like the Edwards, where you can deplete the storage over a few years. In this graph, this is a map of just historical water levels. These water levels up in the outcrop over 50 years in South Carrizo, they haven't changed at all. Even though there's been 200, 300,000 acre feet of pumpage down here in the main part, the artesian portion, that has caused these artesian water levels to decline over time. Here's a map that illustrates this a little bit more. This is a map of Texas that shows historical water level declines. In the Trinity area, we have 800, 900,000 feet of historical declines in some zones. And you have the Houston area with 200 or 300 feet, and this is the South Texas area we're just talking about. But if we shift this and say, what has been the historical change in storage? Here we see a totally different map where only the depletion of storage is mainly in West Texas. In the Trinity and the Carrizo-Wilcox and the Gulf Coast, we have essentially the same amount of water we started with. Billions of acre feet of water, billions of acre feet of fresh water, plus brackish water. Now I'd like to just summarize real quickly some last little thing with conjunctive use, ASR. How does that work in these formations? Well, here, if this, instead of being a pumping well, we're going to use this injection well, and we'll start injecting water down into the system. The pressure around the well will rise. Here we've injected different quality water into this zone and created a storage bubble. When we stop injecting, the pressure around this well is going to go back to where it was, try to go back to where it was before we started. So ASR is not a very good mechanism to try to manage changes in pressure. It works fine to create stored water of a certain amount of quality. It's a storage function. But as far as creating increasing the storage, the only way that could happen is up in the outcrop. And the outcrop is huge compared to how much water you just put in through this injection well or this injection facility. If you were to do this long enough, the state of the developed aquifer, say right here, what you would be trying to do is you'd be trying to rise the water level in the outcrop and increase the natural discharge. So there's this idea that we can take water, excess surface waters, and store it in off-channel reservoirs, and we want to put it into the earth, ASR, to save the evaporative losses. That might work if we don't have a lot of natural discharges, and also depending on the timing of the injection and the recovery. But we also could, in the wrong situation, create more waste and spend money achieving not much at all. On the flip side, if the reduction of storage has occurred and we've reduced natural discharge, we have more ability to store water in these formations than is imaginable. Also, because these regional effects occur with the pressure and the movement of this water, it oozes slowly over broad expanses. We have hundreds of square miles of locations that we could have ASR facilities. So if we think about this, there is the potential, but we've got to be careful about the waste issues and the net effect, the next increase of water. So just to summarize, these are large regional resources. We have the differences in changes in pressure versus the changes in storage. The economics of pressure change are favorable for more development. That's going to cause some conflicts with protection of historic use versus the forces of property rights that are wanting to use more water. And then very, very long term, 200, 300 years from now, we may have some of the nation's largest ASR operations. But it's going to take a long time. Thank you, and I went over a lot of things here. If you have any other questions, please feel free to ask me. I'll be glad to talk to you.
What I'd like to do now is take a few minutes to go up in elevation and then go backwards in geologic time to the Edwards aquifer complexes in central and southwestern Texas. So this is an aquifer complex that is very different both in geologic character, which governs the way that groundwater occurs and flows and is recovered, as opposed to what the dipping aquifers are. So you get a different flavor, and it presents some unique management challenges as well and opportunities. First, one disclaimer that I'll start off with is I know that probably many in this room have been students of the Edwards Aquifer, and that's a topic which could take several days to go through with its history and the complexity. So I'm going to just give it a fairly broad brush treatment just to point out some of the major challenges that and things that govern groundwater flow there. So the map shows here basically the area we're talking about, which includes the Edwards-Balcones Fault Zone Aquifer, one of the major aquifers of the state. Occurs pretty much in an arc shape from kind of central Texas all the way down to the Rio Grande border. It's illustrated in that blue shade. And then the related Edwards Trinity Plateau Aquifer, which is a large complex occurring in the southwest Texas, very much a rural area, very much different in character in terms of water usage and occurrence than the fault zone aquifer. I think to understand really a little bit about the Edwards Aquifer Complex is to understand the topography of the area. So this is a map that shows by color the relative elevations. Of course, the Edwards Trinity Plateau is on the Edwards Plateau, which is an elevated section of land which is bounded by some major river systems, including the Rio Grande. The Pecos River flows through a portion of it, and then the Colorado River systems to the north. And then bounded on the south and east side by the topographic expression of Balcones Fault Zone. So this gives rise to some interesting characteristics of the Edwards Aquifer, at least on the plateau, as well as the faulted nature of the Balcones Fault Zone aquifer, which gives rise to both occurrences of water table conditions and confined conditions, and also drastic changes in water quality as well. So this is a map of, again, the state with the major aquifers in color, but the blue dots that you see sprinkled on are some of the major springs. The first thing that your eyes will be drawn to is the fact that within the central Texas area and then sprinkled throughout the Edwards Plateau are a number of springs. In fact, some of really the major springs throughout the state are draining these two aquifers and have given rise to special both historical use of the water, cultural conditions, and important environmental considerations as well that factor into the management of both these aquifers. This is a map that shows again, the occurrence of the Edwards Balcones Fault Zone aquifer. The dark blue is referred to as the unconfined or water table aquifer. The hatchered area is what we call the subcrop, or what Bob was spending time on, the confined area, which is under Artesian pressure. And this map shows, again, the plateau aquifer, the Edwards Trinity Plateau. One thing you'll notice by the solid shading is much more portion of this aquifer is in outcrop or unconfined conditions. Relatively little, by comparison, is in the submerged or buried confined portions of the aquifer, and this will become an important consideration as we go forward. So a few points about these aquifers to consider. First of all, the character is very different than what the aquifers that Bob was describing, which are basically sand, gravel, clay, silt units. The Edwards are limestone dolomites, they're hard rock. There are sandstone units, sand units within those aquifers, but it really governs the way that groundwater flows differently within those aquifers as opposed to the other units along the Gulf Coast. And that formation is basically what we call the karst condition, which is these hard limestone units. As rainwater percolates through them, they're mildly acidic and tends to dissolve out portions of this rock, which results in the formations of caves and, more importantly, solution channels which groundwater can then flow very rapidly through, as opposed to the very slow flow that Bob was describing in the Gulf Coast units. Water flows very, very rapidly by comparison through the Edwards Aquifer. These aquifers also support a very diverse mix of usage. For a long time, the city of San Antonio depended entirely on the Edwards Balcones Fault Zone aquifer, still does to a large degree. So it supports a good portion of the Austin area and many of the growing cities along the Austin, San Antonio, and westward corridors. Then when you move inland and upwards into the Edwards Plateau, you have much less population, but there's a lot more usage of irrigation, groundwater for irrigation purposes. And of course it extends off into the borders of the Permian Basin, so it supports water needs of the oil and gas industry, which of course this contrasts sharply with the municipal in the east towards more rural and energy production in the west. And of course that has important considerations for how the resource is managed as well. Some additional points, again, in the Edwards Aquifer, the relationship between groundwater and surface water is very apparent, and this is important. I discussed already the fact that springs form largely around the margins of these aquifers where rivers have incised into the rock. But these groundwater resources in these areas also contribute significantly to the flow of rivers. In fact, form the headwaters of several rivers, and in other rivers form a majority of the base flow that you see, or the flow that you see in those rivers. So it's extremely important from a groundwater surface water interaction standpoint. And of course, that then gets us involved with the interesting legal considerations of groundwater as a private property right versus surface water as a state ownership. So that's plenty of adventure in the Edwards Aquifer for those topics. And again, these are some of the significant springs which occur in the area. San Felipe really supplies water to the city of Del Rio. Of course, the other springs listed for the Edwards-Balcones Fault Zone are both ecologically important as well as recreationally and water supply. And then far out in Pecos County and Reeves County in the west, you have Comanche and San Solomon Springs, which are important resources as well, both recreationally and historically. One thing to consider, particularly for the Edwards Plateau, the water levels have been relatively stable over time. Bob showed you the map of water level changes. You probably recall those areas remain blue in color. Really, recharge and discharge have been fairly balanced over time, but you'll see because of the nature of the rock and the karstic behavior and the groundwater usage, you can experience short-term and very rapid changes in water levels. And we'll talk about that in just a second. A few other facts about these aquifers. The first two rows talk about the outcrop and subsurface area. I already pointed out, if you look at the Edwards-Balcones Fault Zone, you'll see that they're both small, and there isn't a great deal of difference between the subsurface and outcrop area. But if you look over to the Edwards Plateau, you'll see the outcrop area is extends over 10 times the area of the subcrop. Groundwater districts cover the vast majority of both those areas, so there's groundwater management that's occurring both in those areas. There's a few exceptions. Probably the one that's been, at least in the groundwater news, most recently is Valverde County, which is the home of the San Felipe Springs, and the Devil's River is not currently governed by a groundwater conservation district. The other information you see there, I'll point to, total storage. Those look like large numbers, but they fluctuate rapidly, and compared to certainly the volume of water that Bob described in the dipping aquifers, much smaller in terms of storage than the vast aquifers on the Gulf Coast and the Creeso-Wilcox. The numbers at the bottom row I alluded to just a minute ago. The percentage of stream flow that you see in those areas that is due to groundwater discharge, highly significant, of course, in the Edwards-Balcones Fault Zone. Really, when we did a study for the legislature a couple of years ago. It's available on our agency website, but we found that nearly 3/4 of the stream flow is due to groundwater discharge. So what's going on in the subsurface is highly relevant to what you see at the surface in those areas. And even the Edwards Trinity Plateau, the majority of water you see in streams is coming directly from the groundwater. So again, an important management consideration. This is a cross-section, so from the left to the right, basically going from west to east. This just gives you kind of the relationship. The green and much of that brown area is the Edwards Plateau Aquifer. It receives recharge from rainfall, probably some local stream flow and so forth. As water flows generally to the south and to the east, it enters into more confined conditions when you get to the fault zone, where it can produce some very spectacular groundwater discharges from wells, and is really a very significant source of water. Interestingly enough, that I'll show in just a minute, water quality considerations also important in the Balcones Fault Zone, because you have in a very short distance, you have fresh water grading very sharply into saline water. So that's another important physical feature that needs to be considered in the management of those supplies to ensure that there's adequate freshwater supplies for the future. What what talk about aquifers would not be complete without a picture of the rock, actually. So this is a picture of Edwards Trinity Plateau Aquifer, a road cut near Kerrville on I-10. And this shows that you can see those dark spots. Basically gives you a picture of how groundwater occurs and flows. It isn't a uniform flow at all times as in these Gulf Coast aquifers where you have this porous flow, groundwater flowing between sand grains essentially. In the Edwards aquifers, you basically have channels or solutions where groundwater is channelized and flows, and you can see those seepage zones emerging out of that road cut there. That is characteristic of the karstic nature, very different animal than the Gulf Coast aquifer, the Creso-Wilcox. And again, posing some, recognizing this fundamental difference is important for groundwater managers to understand. And if there's any place in the state where the term underground river might apply, I'd say it's a term that hydrogeologists generally don't like to use, but that's probably the closest that you'd find that kind of situation in the Edwards because it's highly focused and channelized. Speaking of focused, this is one of my favorite pictures. I have two favorite pictures here. This is a picture from the San Antonio newspaper of a large sinkhole in Medina County. If you ever wondered about recharge, this is it. This is a great picture that shows how streams basically just disappear down large solution cavities feeding directly the aquifer, which gives rise to very, very rapid responses of the aquifer levels to rainfall and drought as pumping occurs. So you see very, very significant fluctuations that can take place that you would not see so much in the dipping confined aquifers to the east. And I just have to conclude a picture like this. This is near Austin, a little whirlpool forming, and I believe Onion Creek, or one of the creeks south of Austin, just showing actually this is a good surface water groundwater relationship slide in the other direction, where surface water is feeding into the aquifer. So I mentioned water quality a few minutes ago. This is a picture again of the Edwards-Balcones Fault Zone aquifer. The pleasant blue tone is the fresh water extending really from southern Bell County down over to Kinney County in the southwest. So you can see it's got a lot of fresh water, but very abruptly transitioning into those yellow and red colors, which are as much as 35,000 milligrams per liter of total dissolved solids, which is pretty close to seawater level salinity. So you can see that the management and production of water in those zones is done very judiciously because of the very abrupt boundary, and it's what's been called many times the bad water line that occurs south of San Antonio. So that's another feature of the aquifer and the scientific complexity that needs to be considered as part of this. You also have water quality variations in the Edwards Plateau aquifer, dominantly freshwater system, but as you look into the north and west, you see those warmer colors representing groundwater that is basically in the brackish to slightly saline zone, and which also corresponds to much of the oil and gas production which is occurring in that area. So many times the oil and gas producers can use the water that's higher in TDS than maybe others, but many of the residents of that area are drinking water and have been using water over the years, which is slightly saline or brackish in quality. I mentioned the highly variable fluctuations occur in the aquifer. This is a graph that shows over time since the mid-1930s up until this year, what we call an index well in San Antonio. The lines really show how the aquifer has changed back and forth during periods of drought. You can see towards the left side in the 1950s in the drought of record, water levels were basically cycling downward, but you can see how it just goes up and down and responds very much to weather, climate changes that occur in that area. So again, a highly fluctuating nature as opposed to some of the dipping aquifers, which are much more gradual in appearance. We also can note that in several cases that discharge from springs and water levels in index wells can be tied together and have been used in the past to evaluate the effect of groundwater on spring flow. The red line refers to spring flow discharge from Los Morris Springs in Kinney County, and the blue line shows, which tracks it, is in a nearby well that has been used as an index to basically help manage the aquifer there. Groundwater use varies quickly. I mentioned this before. In the Balcones Fault Zone, mostly municipal, the dark blue color with some with irrigation forming the rest of it. In the plateau, it's a flipped story. It's basically irrigation with a relatively little or a much smaller proportion of municipal. These numbers show the groundwater pumpage in the vertical column in the middle shows groundwater pumpage in our most recent data from 2015. Edwards Balcones Fault Zone has about 345,000 acre-feet per year. That varies up and down, whereas you get about half that much in the Edwards Trinity Plateau, mostly irrigation. Model available groundwater, I'm just going to mention just briefly, many of you are familiar with the concept. It's a result from a policy decision from desired future conditions. I've included the number for the Balcones Fault Zone. It was a much smaller number, and you'll first look at the comparison of pumpage versus the model available groundwater, which is a policy-based number. You'll say, well, there's a big difference there. Well, I haven't included the amount of water that the Edwards Aquifer Authority is permitted to pump out, which is roughly 400,000 acre-feet per year. And you get that in terms of model available groundwater in the plateau aquifer, much more water, we would say from the manager's standpoint, is available to pump than has historically been pumped. The Balcones Fault Zone is pretty much at capacity. Just looking at desired future conditions and policy goals, most of the areas in the aquifer have drawdown-based goals, but there are several spring flow-based goals. I know that the Clearwater District in the northern part of the aquifer in Bell County and the Barton Springs District also have spring flow-based goals. Index wells have been used. As I mentioned, that J17 well is used to help the city of San Antonio make decisions on terms of water conservation. And then the Barton Springs Aquifer District has also considered and used in the past freshwater and saline water desired future conditions. So there's a number of management styles and approaches that have been used in these aquifers. So with that, I'll wrap up and give you a picture of the Devil's River, which is one of the sensitive rivers flowing from the Edwards Trinity Plateau.